there, deep divers. We're diving into the world of quantum entanglement today.
Sounds exciting.
You've been looking into a research paper?
Yeah.
And some recent news about it, and let me tell you, this spooky action at a distance stuff is really capturing our imaginations, too.
Really fascinating stuff.
We're going to try to unpack what has scientists so excited, starting with the basics.
All right.
Quantum entanglement. It's like two particles are linked no matter how far apart they are. Change one and the other changes instantly.
Right.
What's really cool is that we're going beyond that basic definition today.
Okay.
We'll see how physicists are finding new ways to understand entanglement within materials.
Right.
Even coming up with a simplified formula for it.
Yeah, that's pretty cool.
So what's really fascinating...
Well, what's really fascinating is that physicists at Osaka Metropolitan University have taken a new approach. Instead of just looking at entanglement as a property of a whole system, they're zeroing in on what's happening at a very localized level between individual particles.
This local interaction idea is intriguing.
Yeah.
It's like we're shifting from a bird's eye view to examining the individual threads in a tapestry.
Exactly.
Does that make sense?
It's a more granular perspective by understanding these specific interactions.
Okay.
Scientists can build a clearer picture of how entanglement actually works within materials.
So they're focusing on these strongly correlated electron systems as their testing ground.
Yeah.
Can you break down what that means for us?
Imagine electrons in a system that are constantly interacting almost like a tightly choreographed dance. Their movements are highly interdependent.
Okay.
These strongly correlated electron systems are like a magnified view of entanglement. Because those interactions are so crucial, it gives researchers a clearer lens to study the phenomenon.
Okay, so we've got these entangled electrons in a tightly knit system, but then the researchers go and find the surprisingly simple formula for entanglement entropy.
Right.
I have to admit, that's where I started to get lost.
Okay.
What's the significance of that discovery?
Entropy, in this context, is a measure of how entangled a system is. The higher the entropy, the more entangled it is.
Okay.
And finding a simpler formula to calculate it is groundbreaking.
Wow.
Not only does it make the math easier, but it also allows scientists to study entanglement in a more efficient way.
Yeah.
It's like they've been given a more powerful tool to explore this complex phenomenon.
That's fascinating.
Yeah.
But it sounds like they didn't stop there. They applied this formula to some really tiny artificial magnetic materials and got some results that defied expectations. What happened there?
They were working with materials at the nanoscale, a scale that is unbelievably small, and the patterns of entanglement they found were unexpected and didn't fit with the existing understanding of how entanglement works, especially at such tiny scales.
Okay, now I'm really curious. This is starting to sound like a real mystery. Can you tell us more about these unexpected patterns and what they might mean? So we're talking about unexpected entanglement patterns at the nanoscale. It sounds like this research is really pushing the boundaries of what we thought we knew. Can you elaborate on those unexpected patterns?
Sure.
What were the researchers expecting to see, and what did they actually find?
Well, they were working with these nanoscale artificial magnets arranged in a linear chain, kind of like a microscopic magnetic necklace, and they expected the entanglement between these magnets to decrease as you move further apart in the chain.
That makes intuitive sense, right?
Exactly.
The closer the magnets are, the stronger their influence on each other?
Exactly, but that's not what they found. Instead of a simple decrease in entanglement with distance, they observed these peaks and valleys, these fluctuations that didn't fit the expected pattern.
So it's like there's some hidden force or interaction at play that's messing with those entanglement patterns. That's wild. Can you tell us a little more about this new formula they used and how it led to these discoveries?
The formula itself is surprisingly elegant in its simplicity. It uses the number of up and down spin electrons within a target atom,
Okay.
and the number of corresponding holes or spaces where electrons could be.
I remember you mentioned these holes before.
Yes.
So it's not just about the electrons themselves, but also these empty spaces that play a role in entanglement.
Precisely by analyzing the arrangement and interactions of both electrons and holes, they were able to quantify how entangled a specific atom is with its surrounding environment. And this relatively straightforward calculation opened up a whole new way of looking at entanglement, especially in these nanoscale materials.
This is all so fascinating. We've got this simplified formula that's giving us new insights, and we're seeing these unexpected entanglement patterns. I can't help but wonder, what are the potential implications of this research? Could this lead to advancements in things like quantum computing?
Absolutely. Imagine being able to precisely engineer and manipulate entanglement in materials at the atomic level. That's the holy grail for many quantum technologies.
Okay, so how would that actually play out? Give us a concrete example of how this research could lead to real-world advancements.
Let's take quantum computing. One of the biggest challenges in developing powerful quantum computers is controlling and maintaining entanglement between qubits, the quantum equivalent of bits in a classical computer.
Right.
This new understanding of entanglement, especially these unexpected patterns they found, could offer a whole new set of tools for designing and controlling those delicate entangled states.
So we could see more stable and powerful quantum computers thanks to this research. That's pretty amazing. What about other applications?
Well, quantum cryptography relies on entanglement for secure communication, with a deeper understanding of how to manipulate entanglement, particularly at the nanoscale. We could see the development of even more secure communication methods that are virtually unbreakable. This research could be a game changer for cybersecurity in the quantum era.
So it sounds like this research is opening up a lot of exciting possibilities. We're seeing a potential revolution in computing and communication, all thanks to a better understanding of how entanglement works at the tiniest level. It's mind-boggling. But before we get too carried away with all the potential applications, I want to go back to those unexpected patterns they found.
Okay.
They really seem to challenge what we thought we knew about entanglement. What are the scientists saying about why those patterns emerged?
There's a lot of speculation right now, but no definitive answers. Some believe that at these incredibly small scales, factors beyond just physical distance are playing a significant role in how entanglement behaves, things like quantum fluctuations, the geometry of the material itself, or even some unknown quantum principles that we're just beginning to glimpse.
This is where it gets really interesting for me. It's like these findings are hinting at a whole new layer of complexity in the quantum world. Could you expand on some of the theories scientists are exploring to explain these unexpected results? What kind of new physics might be at play here?
Well, some physicists are suggesting that our current models of entanglement might need to be refined or expanded to account for these nanoscale phenomena. Others are proposing entirely new theoretical frameworks to explain what's happening. It's a really exciting time because these findings are pushing us to re-examine our assumptions and explore the boundaries of our understanding of quantum mechanics.
So we might be on the verge of some major breakthroughs in our understanding of entanglement and potentially even quantum mechanics itself. What kind of research or experiments do you think will be crucial in the coming years to shed more light on these mysteries?
Replicating these findings with different materials and systems will be crucial to see if these unexpected patterns are a universal phenomenon at the nanoscale or if they're specific to certain materials. And of course, developing more sophisticated theoretical models that can account for these complexities will be key to truly understanding what's going on.
It sounds like we're at the beginning of a very exciting journey of discovery in the quantum world. This research is opening up so many new questions and possibilities. What are your thoughts on the future of this field? Where do you see this research leading in the next decade or two?
Well, it sounds like we're on the brink of a new era in quantum research. These findings about entanglement at the nanoscale are really shaking things up. It makes me wonder about the long-term implications. What kind of impact could this have on our technological landscape in the coming decades?
Yeah, the potential is truly vast. If we can understand and harness these unique entanglement behaviors, it could revolutionize fields like quantum computing, communication, and sensing. We're talking about a huge leap forward in technological capabilities.
Can you paint a picture for us? What might some of these future technologies look like in practice?
Imagine quantum computers that can tackle problems currently deemed impossible for even the most advanced supercomputers we're talking about, breakthroughs in medicine materials, science, artificial intelligence, and so much more. It's almost hard to fathom the possibilities. And what about communication? How could this research impact the way we share information in the future?
Imagine a world where communication is not only ultra-fast, but also completely secure thanks to the unbreakable nature of quantum entanglement. This could revolutionize everything from online banking to sensitive government communications.
So we're talking about a future with more powerful computers, unhackable communication networks, and who knows what else. It sounds incredibly exciting. But I also imagine there will be challenges along the way. What are some of the biggest hurdles researchers will need to overcome to make these futuristic technologies a reality?
One of the biggest challenges will be scaling up these nanoscale discoveries to a level where they can be practically applied. We need to figure out how to control and manipulate entanglement in larger systems, not just in these tiny, precisely engineered materials.
That makes sense. It's one thing to observe these phenomena at the nanoscale, but quite another to harness them in a way that can impact our everyday lives. Are there any other roadblocks you foresee?
Developing new theoretical frameworks that can fully explain these unexpected entanglement behaviors will be crucial. We need a solid theoretical foundation to guide our technological advancements, and of course there will be engineering challenges in building the sophisticated devices and systems needed to exploit these quantum phenomena.
It sounds like a monumental task, but one with incredible potential rewards. I'm curious, what are you personally most excited about in terms of future research in this field? What questions are you most eager to see answered?
What really intrigues me is the possibility that these findings are pointing to new, undiscovered principles of quantum mechanics. Are we on the verge of expanding our fundamental understanding of the quantum world? That's a question that keeps me up at night.
That's a fantastic point. It's not just about the technological applications, but about expanding the very frontiers of human knowledge. This is why we explore, why we push the boundaries of science. It's about uncovering the mysteries of the universe and understanding our place within it.
Exactly. It's about the pursuit of knowledge for its own sake, and the incredible possibilities that often emerge from that pursuit.
Well, dear listeners, we've come to the end of our deep dive into the captivating world of quantum entanglement. We've explored the basics, delved into groundbreaking research, and contemplated the mind-blowing implications for the future. Remember, the quantum world is full of surprises, and what we've uncovered today is just the tip of the iceberg. Who knows what other wonders await us? As we continue to explore this fascinating realm, keep questioning, keep learning, and stay curious, because the journey of discovery is far from over.